So now we've seen the general shape of the sine function or the sine wave, and we've seen also that it repeats every 2 pi units in the x direction, okay? Lots of different properties now start to develop about the sine function. We've seen a couple of them. First of all, the domain is all real numbers because it extends indefinitely in the x direction. The range runs from -1 to 1 because it's pinned in vertically between those two values. And we also know that there are positive and negative values, and there's some symmetry here, sort of symmetry between the two. Now, so a couple things I want to point out. The first thing is that the period is 2 pi. Again, that's the distance over which one wavelength is mapped out. And it could start, you start at the origin, or start on the x-axis and go to the x-axis on the other side of the mirror image. But you could start anywhere. You could start up here at the peak and get to the next peak, and it's going to be another 2 pi distance between them. So any two consecutive points on the wavelength would be 2 pi units apart. In addition to that, we have what I would call the 5 key points on any sine wave. They are the 3 x-intercepts and the maximum and the minimum, okay? So we have our 5 key points. When plotting the graph of any sine wave, and we're going to be altering the sine function, doing some stretching and shifting and other things like that, reflecting as well. And so when we do those things, I think it's most important to be able to remember these 5 key points and find those. Once you've found the 5 key points, your 3 intercepts, your max and your min, you can really sketch the graph just kind of using a smooth curve going between them, okay? So those 5 key points are going to be important. Now, to find the intercepts, generally the intercepts are found, at least for the regular, just the sine of x, the intercepts are all going to be at integer multiples of pi. Notice 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, and so on are going to be intercepts, and going negative, you have negative pi, negative 2 pi, negative 3 pi, and so forth. So integer multiples of pi are going to be the x-intercepts. Okay, so the x-intercepts are going to be integer multiples of pi, or the way that we usually represent that is n times pi, where n is an integer. Okay, so n times pi where n is an integer. Again, we're really focusing on the sine itself, sine of x, sort of our basic sine function. My 5 key points then, because of those x-intercepts and the fact that the max and the min are halfway in between, so that'd be pi over 2 and 3 pi over 2, or half a pi and 3/2 of a pi. The 5 key points then are going to be where x is equal to 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those are our 5 key points, where the first, middle, and last are going to be the intercepts. The second one is the max, the third one is the min. Now, when we start to move these things around, shift them and stretch them out, those 5 key points will change, but there's a nice method for finding them. You start at 0, add the period, that's your 2 pi, and then you start cut that in half, cut that in half, cut that in half, and you'll be able to find the other points. We'll go through an example later of how that lays out. There's also some very interesting symmetry here. Some of you may have seen graphs before, like parabolas in an algebra class that have like y-axis symmetry, right? On a parabola you might have, some sort of symmetry here around the y-axis. And of course there are many other functions that have many other types of symmetry to them. The sine function has symmetry that we would call the origin symmetry. What's interesting then is that any point on the sine graph can be what we call reflected through the origin and a symmetrical point found on the other side. So if you have a point up in the first quadrant, upper right, it has a sort of mirror image in the lower left third quadrant, right, going through the origin. And really you can do this with any point on the graph. If I reflect it through, this is gonna be a hard one to hit. Oh, I don't have a similar point. But if I go the same distance on the other side, I should have another point on the graph over here somewhere, okay? So you can reflect points through the origin to get another point. So we say that this has origin symmetry. Origin symmetry. And we have a name for all functions that have origin symmetry. They're called odd functions. Okay? And with all odd functions or origin symmetry, it is always the case that if you take a function value, I'm not sure how I want to draw it, maybe I'll put it over on this side. Think about extending this back left. If I take a function value up here on the upper right, there'll be a mirror image on the lower left. And if I take one on the lower right, there'll be a mirror image on the upper left. And so if I were to, let's say you had a positive x and a positive, positive x and positive x, f of x, then the mirror image would have a negative x and a negative f of x. Or if you have positive x and negative f of x, and the mirror image would be negative and positive. And so it ends up changing the sign on both the input and the output. If you change the sign on the input, it changes the sign on the output. Okay, so positive positive results in negative negative. If you had a positive negative, it would be a negative positive. So the signs both change. And so a way to represent that using the function notation here, sine of x, is to say that if you were to input a negative x, the output will be the negative of the sine of x, okay? So if you change the sign on the input, it changes the sign on the output. Negative input creates a negative output, essentially, okay? In a more general sense, as function notation, all odd functions could be represented as f of negative x equals negative f of x. Okay, that's a longer discussion that you might have in, say, a college algebra course on all general functions that have origin symmetry. Okay. Okay. So anyway, that's going to be the case. And now this is a true property for all sine values everywhere. Okay, so not just pertaining to the graph, I guess, but if we just think about inputs and outputs for sine, if you change the sign, S-I-G-N, of the input, it changes the S-I-G-N sign of the output. Okay, don't confuse the positive negative sign with the sine cosine sign. That is very confusing. I hate that it's the same word, but it is. So anyway, let's continue. So, another thing I wanted to mention is that the different quadrants show up on the graph here. The interval from 0 to pi over 2 corresponds to all values in quadrant 1, okay? And then all the, from pi over 2 to pi represents quadrant 2. So your quadrants are actually, so they show up here on the graph, okay? So then you got pi over 2 up to pi is, of course, quadrant 2, and, whoops, pi over, that'd be just pi. So pi to 3 pi over 2, that corresponds to quadrant 3 on a circle, right? You have your values in each of those 3 quadrants there. And then 3 pi over 2, to 2 pi represents quadrant 4 sine values, okay? What what else do we have here? A couple other really interesting points, and I'm going to have to start erasing some of this to make some room, is the period, not the period, the amplitude. The amplitude of a sine wave. Now, the amplitude of anything is just the height from its center axis up to the top. If you think about a wave, the amplitude in this case, the center axis up to the peak, or from the center axis down to the minimum, is going to be the amplitude. Okay, so in this case, the amplitude is this height of 1. Okay, it's sort of half of the overall height of that wave. What's interesting is the amplitude is always going to be the leading coefficient of the sine. So if I were to, let's say I doubled the sine, I said 2 times the sine of x. Well, all that does is it doubles all of your outputs, and so it changes your max to 2 and your min to -2 because you're just multiplying everything by 2, right? The output of a half raises to 1. The output of -half goes down to -1, and so it just kind of stretches your graph out by multiplying. And so that's going to be sort of a general principle then, that if you had y equals, we'll call it a times the sine of x, a is just a coefficient or a multiplier there, then that a value represents the amplitude, a for amplitude, I suppose. Okay, so a is the amplitude. Now, of course, a could be a negative number, and amplitudes, we tend to represent them positively. So I might throw an absolute value on there. Okay, so if a was negative, the negative actually results in a flip of the graph, but the amplitude would still be the absolute value. So an example, let's see here. An example very simply would be if you had 5 times the sine of x, then the amplitude is 5. And the graph then, you have the same wavelength or same pattern from 0 to pi to 2 pi. The difference is that now the maximum is at 5 and the minimum here would be at -5. Okay, so that's what you get if you had a 5 times the sine of x. Same period, but you've stretched the graph out vertically by a factor of 5. Okay. An amplitude is essentially a vertical stretching of the graph. Think of it being like an elastic, rubber band or something. You could stretch it out. So this is what we would call a vertical stretch. Okay. Now you can also have what we call a reflection, a vertical reflection. You may have seen this before, like I said with parabolas a moment ago. If you had a parabola opening up, its leading coefficient is positive. If the parabola opens down, you may have seen this before. Parabola opening down has a negative leading coefficient because you've reflected it across the x-axis. Well, here you can vertically stretch, you can also vertically reflect. So when a is negative, and how do I want to write this? I should write it all out. You have a vertical reflection. Okay, so you end up flipping the graph upside down. So if I had a negative, if I tack a negative on that sign, then my graph just comes down instead of up. Okay, so it just reflects the whole thing, like spinning it around the x-axis essentially. All right, okay. All right, continuing on. So that's our amplitude idea, our amplitude and reflection. The other thing is the period of the graph. So multiplying on the outside of the sine changes it vertically, shifts it or stretches it vertically. Multiplying on the inside the x here, is what will shift, or I'm sorry, not shift, stretch it out horizontally, okay? So it'll change the period. It'll either lengthen the period or compress the period. To do that, I'll get rid of some of this stuff. I don't really need this. So to do this, consider this idea that the period is always takes the input from 0 to 2 pi, right? So when the regular sine of x, you take the input and put it between 0 and 2 pi to get the period, right? Okay. Well, if you were to change, in order to change the period, you would have to multiply that x by something else. So for instance, if I had, let's say y equals, 6, I'm sorry, let's do a sine of 6x, okay? Then one period is mapped out when the input, the entire, not just the x, but this entire angle. Sometimes we call this the argument of the sine. It's the entire expression inside the sine. So I'm going to call that, I'm going to name it the argument. Some people have other phrases for it. I'm going to use that phrase. When the argument is between 0 and 2 pi, you get one period of the graph. And so that means that if 0 is between, or if 0 is less than or equal to 6x is less than or equal to 2 pi, you would have one period. Well then, what would x have to be? Well, the x values, if you divide all three parts of this inequality by 6 to solve for x, still have a 0 on the left, but now I have an x in the middle, and 2 pi over 6 is the same as pi over 3. And so now what I've done is I've created a period of pi over 3. From 0 to pi over 3, the x value maps out a single wavelength, right? So now, on my graph, that's my marker's starting to fade, my full wavelength would be mapped out between 0 and pi over 3 rather than 0 and 2 pi. Then, like I said before, the important thing is to be able to find the 5 key points. Well, I've got the 2 endpoints just from this inequality. The other 3 points are found simply by cutting things in half. There's a variety of ways you could do this. You could cut the period, divide it by 4, and then add from one end to the other. I like to find averages. So that's just my personal preference on this. So the way that I would calculate this is I would take the average of 0 and pi over 3 to get the number directly in between. Well, you know that an average is found by just adding the values and dividing by 2 if you have 2 of them, right? So I would take that average I would just take 0 plus pi over 3 and divide it by 2. That gives me the average. That gives me the number in the middle. Now 0 plus pi over 3 is just pi over 3. And when you divide by 2, remember copy dot flip, it's like multiplying by a half. So pi over 3 times 1/2, same thing. And when I double the denominator there, I get pi over 6. So pi over 6 is in the middle. And that kind of makes sense, right? Half of a third is a sixth. So pi over 3, half of it is pi over 6. If I wanted to cut that in half again, I'd be at pi over 12, right? It'd be double the denominator. So I could go through this process again, averaging 0 and pi over 6, but I know I'm going to get pi over 12. It's doubling the denominator, so there's my other value. And now the one in between, well, if you think of them as multiples of pi over 12, you have 1 pi over 12, 2 pi's over 12, 3 pi's over 12. So this should be 3 pi over 12 here. And again, you could find that by averaging, if you couldn't just count by twelfths, you could average, you could take the average of pi over 6 and pi over 3, which is a little bit longer process. Add them together and divide by 2. Of course, you need a common denominator, so you kind of have to go through these fraction things. Multiply by 2 top and bottom. You have pi over 6 plus 2 pi over 6. Right, multiply top and bottom by 2. Divide that by 2. This would be 3 pi over 6 all over 2. The 3 pi over 6 actually reduces. Is that right? I feel like I did something wrong there. Pi over 6, pi over 3. Average them. Oh yeah, because 3 pi over 12 isn't simplified. I'll come back to it. Okay, it's not matching up in my head. That's okay, it's going to. So here I reduce. 3 over 6 is 1/2. So that's pi over 2, all over 2. Again, copy dot flip. Pi over 2 times 1/2 is pi over 4. And remember, 3 over 12 is 1/4 if you reduce it. So I would actually rewrite that 3 pi over 12 as pi over 4, which of course is equivalent to 3 pi over 12. Okay? Okay, so pi over 4 is that extra point. So I've got my 5 key points in here now. Again, those are not super easy to find. You are going to become probably a fraction expert, hopefully, by the time we're done with these. The fractions usually aren't crazy, and sometimes it's nice to just ignore the pi, right? So you could just think of these as like 1/6 and 2/6 added together makes 3/6. Just ignore the pi and tack it on at the end. That could work as well if the pi confuses you, okay? Okay, so in the next video, I'm going to show you just a couple examples. After I clear the board here, I'm going to show you a couple examples of how to graph the sine, and then we'll talk about the cosine for a few minutes.